right. Hello, everyone. Good morning, good afternoon, good evening, wherever you are in the world. Thank you for joining us today. My name is Sarah Alspaugh. I will be your webinar host, and I'm coming to you live from Cincinnati, Ohio, here in the U.S. As you probably know, Siemens is a very global company, so we always love to hear where our attendees are joining us from. So if you don't mind, take a minute to say hello in the attendee chat and let us know your location. Before we begin, I'm just going to have a few housekeeping items. I'd like to officially welcome you to our webinar, How Northrop Grumman Leverages Simcenter for Space Robotics Success. All right, a little bit about Siemens Digital Industry Software. Siemens Digital Industry Software helps organizations of all sizes digitally transform using software, hardware, and services from the Siemens Accelerator Business Platform. Siemens software and the comprehensive digital twin enable companies to optimize their design, engineering, and manufacturing processes to turn today's ideas into the sustainable products of the future. From chips to entire systems, from product to process across all industries, Siemens Digital Industry Software accelerates transformation. All right, well, I would like to welcome and introduce our speakers for today. With us, we have Jens de Boer and Daisaku Inoyama. I won't take any more time from them. Jens, I know you're going to kick things off. Real quick, attendees, if you want to read more about them or read their bios, you can click the little blue arrows in the bios widget on the left-hand side to read more. All right, well, welcome, Jens. I will turn things over to you. You now have the floor.
Thank you very much. Good day to all of you, wherever you are. My name is Jens de Boer. I'm based in Leuven, Belgium, and I take care of the aviation and space segment within the Simcenter portfolio. In the next 10 minutes, I will be taking you through that portfolio, which brings together all our simulation and test solutions. While doing so, I will share a number of examples of how we can contribute to spacecraft performance engineering and help you launch and evaluate the performance of your products before building them. I'll kick it off with a short outlook on the space market. After that, we will introduce the various physics inside the Simcenter portfolio and show you how together they provide value when solving engineering problems. And after those 10 minutes, I will hand it over to Daisaku for his section on the work Northrop Grumman has done with our portfolio. First and foremost, let's take a look at the space industry just to get our minds settled. To do that, I've taken this graph from McKinsey, and it shows that by which metric you take, the space industry is booming. What's important for the context of our webinar is that we see both an increase in the number of startups, an increase in the number of satellites launched, but also a decrease in the cost of a satellite and a decrease in the cost of launch. It means that overall, this means that yes, the space market is booming, but it's also becoming more competitive. So when you're a startup, it means that you want to launch faster, and these startups are rethinking the way they do their development processes and how simulation and test can be part of that development process. Established companies, on the other way, are pursuing new activities, and they as well need to get their satellites in orbit faster and at lower cost. This is again an area where an intelligent combination of simulation and test can help to improve the time to market of your products. The Simcenter portfolio is very well positioned to support the space industry in keeping this boom ongoing, as it provides both simulation and test capability around a wide range of physics. Within the Simcenter portfolio, we cover structural, fluids, thermal, electromagnetics, acoustics, and chemistry. And when we align that on spacecraft performance engineering, it means that we can efficiently cover propulsion performance. We can look at structural, thermal, and robots engineering. We can look at electromagnetic performance, testing, verification, and qualification, and we help ensure the safety and mission assurance of the satellites and launchers. We typically also articulate a number of consistent values along this application. The first one is front-loading simulation. We increase decision confidence by front-loading simulation by facilitating and promoting more automation and standardization. We help exploring the possibilities. We enable insights by exploring the possibilities, by linking together engineering models from different sources with different levels of fidelity from the start. We help innovate. We impact speed and agility to innovate at a higher rate by maximizing value-add engineering and minimizing overhead. And last but not least, we ensure that the simulations we do are credible by enabling full traceability and alignment, and by linking to overall program processes like MBSE, like verification management. In the next few minutes in this webinar, we will look at each of these value statements, and we will show an example of how we help do that. We start on the right-hand side with credible simulations and talk about how they are performed in full alignment in a traceable way with test, and how this can help accelerate the qualification testing process. We do that, we assure these credible simulations by bringing together simulation and test like nobody else. Historically, we have a strong position in structural dynamic testing and simulation, and we have invested in solutions that help de-risking the tests done and correlating the results afterwards. Recently, we have led the way in reducing the cost of acoustic qualification testing by bringing to the market a set of simulation and test products that enable direct field acoustic noise testing. And we have one of the contents we have provided. You can also find the link here below that talks about what we do in that area of acoustic qualification testing, how we do direct field acoustic testing, and talks about the recent master class we did at our premises in Leuven, where we actually did direct field acoustic testing on an actual satellite provided by ESA. So that's a very interesting read if you want to follow up on this webinar. We continue to mature this hybrid use of simulation and test to more and more move to a simulation-driven way of product development, where targeted tests are done to validate the simulation models and the simulation-driven approach that has been done up front. Why do we do that? Because ultimately, the simulation-driven development approach, which is supported by a credibility assurance framework, allows us to already on the left side of the V, with confidence, check off certain requirements, such that when we go into actual certification and qualification, we will be able to call the satellite fit for purpose earlier. Within the Simcenter portfolio, we have all the tools, methodologies, and processes in place to help you deploy such a credibility assurance framework. Ultimately getting your satellite to launch faster. A second value point is front-loading simulation. In the following example, I will show you how we help facilitate decision confidence by front-loading simulation through a better, more efficient use of automation and standardization. The example I've chosen for that comes from NASA Goddard Space Flight Center and talks about the domain of safety and mission assurance. Also, that case is documented further in a webinar we've done together with them. So as a follow-up of this webinar, you can follow that one. And it talks about how NASA Goddard Space Flight Center has deployed with our tools, with Simcenter, a model-based analysis approach for reliability, availability, maintenance, and safety analysis. By doing that, they are able to run, document, report on several failure and analysis ways from one model. So they can generate one failure analysis. They can generate from a single model different failure analysis reports instead of the disjointed use of Excel that they did in the past. Ultimately, that allows them to increase the confidence they have in their design through a faster understanding of failure modes, a better understanding of the effect that these failures have, and their criticality. A third value point I want to touch on was exploring the possibilities and how we enable insight by help you explore the possibilities by using different engineering models together to represent the complete physical behavior of a system. The example I have selected here is a system where we predict the deployment and positioning of solar panels as a megatronic system combining multi-body simulation to capture the flight dynamics, together with a system simulation model for the power actuators, which is linked to a control model for control optimization. The power of the Simcenter portfolio lies in the fact that we don't optimize on a subsystem alone, be it the dynamics of the satellite, the power actuators of the control system, but optimize across the whole mechatronic simulation system. So we avoid to have a global optimum, but come through global optimum. And Daisaku will also talk a little bit about that later on. The fourth value point, and the last one, is how we help innovate at a higher pace by removing non-value engineering tasks to come to engineering results faster, which is in the end what we want to get to. The example selected here comes from Mynaric. So Mynaric is a company that develops laser terminals to provide secure large bandwidth communication. These instruments need to be very precise. So Mynaric creates detailed simulation models that accurately predicts the thermal and structural performance of these models, because that performance determines the accuracy of the positioning of the laser terminal. In the past, they had to use different tools for that, and there was a complex exchange of information, was time consuming, a lot of overhead in the process, which of course is not what you want. By moving to the Simcenter portfolio, they were able to build up one single model for thermal structural simulation, removing all the time consuming rework and ultimately reducing their modeling time by 83% to get to, which allows them ultimately to get to the market faster. So you can find the more information in the use case we've written together with them. So the link is here on the slide. It's also part of the resources we have shared with them, we have shared with you. To conclude, I'd like to emphasize that our simulation and test solutions, part of the Simcenter portfolio, are an integrated part of the accelerator portfolio. So we bank on that backbone that is given by the accelerator portfolio within Siemens. And it's also backed up by our support and services organizations, which allow you to deploy the change for the better that we provide at scale. As a last note, please be aware that this is mostly for the US people on the line, that we will be hosting a user group meeting in Denver, Colorado on June 19th, specifically for the more Simcenter 3D oriented folks. If you're interested to join that, please contact Katrien Horak. Her email address is on this slide, which we will provide afterwards, and she will be happy to provide you more details. With that, I would like to pass it on to Daisaku from Northrop Grumman, who was so kind to present with us today.
Right, good morning or good afternoon, depending on where you are. I'm Daisaku Inoyama, a manager of multi-body dynamics team at Northrop Grumman Space Systems. Today, I'm going to present how Simcenter 3D is being used at Northrop Grumman for various space vehicle missions, including robotics missions, and share our Simcenter 3D success story. Right, agenda. In this presentation, I'm going to go over how multi-body dynamics, or MBD, is being applied for space vehicle simulations. More specifically, how Simcenter 3D motion is being used to simulate on-orbit servicing operations that include robotics and complex mechanisms. I will also describe what components or engineering components go into those simulations. Next, I will present use case from past and ongoing developmental programs where Simcenter 3D was used extensively and successfully. Mission Extension Vehicle, or acronym MEV, is the first robotics vehicle that we launched. The image of the MEV is shown on the right. In that picture, the black box attached to the satellite is the Mission Extension Vehicle. We'll go over that more in detail when we get to the use case. Mission Extension Pod, or MEP, and the Mission Robotics Vehicle, MRV, the next generation servicing vehicle. I will go over that more in detail later on in the presentation. I'm also going to go over how Simcenter 3D is contributing to in-space refueling program. Test and model correlation is an important process in creating simulation digital twin. I will go over that detail or briefly later on in the presentation. Finally, I will talk about digital transformation and what we are doing to make the simulation digital twin more reliable. So before we go into depth, not familiar with what Northrop Grumman does, we are one of the leading aerospace technologies companies. We work on a variety of products for government and commercial customers. I work with 95,000 talented colleagues to solve toughest problems for our customers every day. For today's webinar, we are focusing on space vehicle simulations, but what I'm presenting should be applicable to many other areas of engineering. Right, MBD application for space vehicles. Multi-body dynamic simulation for space vehicle is very different compared to simulation for ground-based systems. The picture shown on the right is the mission extension pod held by mission robotics vehicle approaching client vehicle. As you can see in the picture, the space vehicle's slender deployables such as solar arrays and antenna boom that can get excited very easily in zero-G vacuum environment. Those flexible bodies often represent largest part of the total inertia of the vehicle. So once it starts oscillating, its impact could be significant. If the mission involves robotics or complex mechanisms, as well as the interaction multiple bodies due to the operation, such as the one shown on the picture, the simulation becomes very, very complex, as you can imagine. My team worked with Siemens experts to make this highly nonlinear simulations possible. And today, MBD is a key element of the on-orbit servicing programs at Northrop Grumman. The overview on-orbit servicing simulations. On-orbit servicing missions involve operations of mechanism robotics on orbit. We use MBD simulation extensively to look into various aspects of the operations, such as structural loads, structure controller interaction, vehicle reaction, and much more. The simulation is extremely important here. Of course, we perform ground testing extensively to understand the robotics and mechanism operation. But after all, the ground test is performed on the ground, and it is not possible to fully replicate the space environment. In the simulation, however, we can replicate space environment, and therefore it becomes very important tool in validating the system. During developmental stage, we can use simulation to conduct sensitivity and reliability study to guide the design and to make important mission decisions. Simcenter 3D motion model of the on-orbit servicing operation look like the picture on the right. It is the model of MRV capturing MEP. Again, we will talk more about this particular use case later in the presentation. There are multiple engineering disciplines that go into the simulation. We have mechanisms, structures, vehicle control, and robotics. The multiple engineering functional team work together to create the simulation digital twin, and that is made possible by Simcenter 3D Suite. Now, let's talk more about what goes into on-orbit servicing simulations or creation of simulation digital twins. This is a little bit of a high chart, but I will go over this quickly and concisely as possible. The first component is the MBD. It includes model of vehicles involved, mechanisms, and contact dynamics. In this instance, this is accomplished by Simcenter Motion. Next part is the structural flexibility. it is presented by motion flex bodies generated from finite element model that is accomplished by Simcenter Nastran. The vehicle controller and robotics control can be represented by Simcenter AIMSIM and or Simulink model. Those four components are combined together to create a simulation. Now that's one simulation. And at this point, there are so many input that we need to apply to the model and so many output to track. We also need to conduct design exploration, such as sensitivity studies and design optimized tool like Simcenter Heat can make that happen. So I guess main takeaway here is that MBD simulation of on-orbit servicing operations requires elaborate networking of various engineering disciplines. We accomplish that by utilizing Simcenter 3D Suite. Now, going into the use case, first servicing vehicle that we developed is called Mission Extension Vehicle, or MEV. A picture of the spacecraft shown here is the MEV. The mission of the vehicle is to dock with the client vehicle on orbit and provide attitude control to extend the mission life of the client vehicle. After separating from launch vehicle, it performs an operation called RPOD, stands for Rendezvous Proximity Operation and Docking, and approaches the client vehicle and finally dock with the client vehicle. The small picture on the right, the dark picture on the right, are taken by on-orbit cameras on MEV approaching client vehicle. In this particular case, I believe MEV is looking at Intelsat 901. This vehicle has a specialized mechanism at the top of the vehicle that is used to latch onto the client vehicle from a close proximity and then pulls into complete docking. There are two MEVs in service today. I believe the first one was launched back in 2019. The vehicle is also capable of undocking and go serve another client vehicle if it needs to. We perform extensive simulation for MEV docking operations, considering various docking scenario and parameter variations. The picture shown on the right was taken by on-orbit camera of MEV. You can see that the mechanism extends out to client vehicle engine nozzle to capture and then pulls into docking. As you can imagine, there are so many uncertainties in this session. Two vehicles can have relative offset as well as velocity, both in translation and rotation in 6 degrees of freedom motion. The contact parameter between mechanism and nozzle can be uncertain, as well as how the deployable will behave once mechanism makes contact and start performing the operation. The simulation can be used to provide answers to those uncertainties and minimize mission risk. The picture on the left is the Simcenter motion model of the MEV docking operation. It is essentially a simulation digital twin that includes full details of the docking mechanisms, flexible structures to assess structural loads, and then vehicle dynamics under various conditions. The next generation servicing vehicle called Mission Extension Pod, MEP, and then Mission Robotics Vehicle, RV. MRV has a robotics arm on top of the vehicle. It can be used to install MEP to client vehicle, as you can see in the picture on the right. In this picture, the MEP is being held by a robotics arm of the MRV. The robotics arm can also be used to perform inspection, grappling onto the client vehicle to do the repair, and also debris removal, and docking with client vehicle with no standard interfaces using a specialized tool and effector tool. the end effector can have variety of tools to do many types of operations. The robotics arm was supplied by partner organization, Naval Research Lab. And in the picture, you can see that the MEP is a dish-sized vehicle that is installed onto client vehicle using a specialized docking mechanism while being held by MRV at the close proximity to the client vehicle. Once installed, it acts as a propulsion module to extend client vehicle missions. But before getting to docking operation, MEP and MRV goes through complex operations. MEP simulation is used to verify all those operations. Here is the simulation of the MRV capturing MEP using a specialized capture tool called PCS, or Pod Capture Tool, developed by MDA. The picture of the same or similar tool that I found in the conference paper is shown on the right. In the picture, the person is holding a grapple fixture that goes onto MEP, and the cylindrical tool with the tool. Cylindrical tool, it goes onto the end effector of the robotics arm of the MRV, which is shown on the.
Thank you for watching. To learn more about this topic, check out the links in the description. And if you enjoyed what you saw, like the video and subscribe to the channel.